All right, great. So welcome everyone to Symmetry Seminar in 2024. It's a great pleasure to have Nat to talk about non-invertible SPT order in a group-based cluster state. Please take it away.
Thank you, Sakura, for the invitation to give a talk here. So I understand this is a sort of broad audience, so I'll try my best to talk about to explain what we were trying to do in this work. And this work is a collaboration with Chris Fescherson and Victor Albert. They're both at Maryland, and we're sort of a lattice people. So I'll try my best to explain sort of our take on trying to understand non-invertible symmetries, and in particular non-invertible SPT order. The main reference we just put out last month, and there are a couple of related references, which is the model we analyzed was first introduced in this paper about 10 years ago by Bro, where he introduced this generalized version of a cluster state from the group Z2 to finite groups. And he also conjectured that it was an SPT phase protected by non-invertible symmetry. So it was quite an advanced claim back then. What we did was we took this example and just analyzed the 1D case, 1 plus 1D, and sort of try to understand all these microscopic features better. And the tool we used that allowed us to understand more about these came from some of these works. One is how to generalize Pauli operators to the group-based versions, which was done in this work by Victor and others. And also, one of the things I'm going to try to highlight today is how these generalized cluster states are closely related to the notion of gauging. Okay. So let me try to motivate a bit, and I'm going to apologize in advance for the lack of a number of references here. But what I'm going to try to focus on is non-invertible symmetries on the lattice. And there are many ways one can try to approach this, for example, in order to understand this non-invertible symmetry rep G. So for example, you can start with a group symmetry G and gauge a subgroup to get a dual, potentially non-invertible symmetry. And at least the first reference I think I learned this from was the paper by Lakshya and Yuji Tajikawa. Recently, there's also this paper by Clement and Apoorv, which also discussed this on the lattice explicitly. In particular, by gauging the symmetry G, this gives you a dual symmetry called rep G. Another way to approach this is by explicitly starting from the edge of a quantum double and trying to extract out what the symmetry action looks like on the boundary. And this is sort of, in modern terms, you can think of this like a symmetry TFT perspective. And on the lattice, this has been studied. On the lattice, this has been studied by this paper by Victor that I mentioned earlier, who tried to look at one specific boundary of the quantum double. In this paper, they only looked at the one where the symmetry realizes as G, but you can also generalize it to potentially get this rep G symmetry that I'm going to talk about. And another way you can analyze this is you could start from a Hopf algebra directly and try to write down a lattice model. And the reference I know is first done by Sansei here. There are also some other works which would go beyond Hopf algebras. For example, I forgot to write down that was done lately by Nadi and Shuhang, which does this for the rising symmetry on the lattice. And maybe one of the talks really was to point out that it looks differently from the one we expected to, Okay. So here, the goal of my talk is to just analyze one particular lattice model, which is this generalized cluster state. I'm going to show that it's an SPT protected by G times rep G. And basically what we're going to try to do is beat this model to death. Of course, today I might not have time to go over all the aspects we talked about in the paper, but that's going to be the goal, to hopefully get a flavor of what this model looks like. Okay. So the outline of my talk is I want to first quickly review the Z2 cluster state. And I want to explain how this cluster state is closely related to the notion of gauging the Z2 symmetry. From that, I want to generalize this cluster state to the G case. And for that, the tool we'll need is this group-based Pauli operators. And based on this would actually give us a lattice representation of rep G, which is a nice matrix product operator representation. From that, I'm going to hope to talk about the three aspects, depending on time and the order. Let's see how many I will get through. One is I want to talk a bit about what does it mean for an SPT to be non-trivial, at least from the perspective of a lattice. What does that mean? And then I'm going to talk about aspects of SPT, which we usually think of when we think of 1+1D SPTs. For example, edge modes, we generally describe projective representations for group-based SPTs. What does that mean for non-invertible symmetry in this example? And also topological response in this case. If you thread a flux, usually you get some charge. How does that work in this example? Okay. So let me get started. So let me first start by being super pedantic. And I just want to talk about a Z2 symmetry on the lattice, get the notation very clear. So for example, when we talk about Z2 symmetry on the lattice in 1+1D, we usually talk about transverse field's Ising model, and where the Hamiltonian has a transverse field, and also, sorry, an Ising term and a transverse field.
So
and
is there a
yes.
motivation to look at G times rep G instead of rep G or some other more general non-invertible symmetry?
Okay, yeah, let me mention that. So the reason will become clear when we relate this cluster to the state to gauging. So the cluster state is the state protected by Z2 times Z2 symmetry. And you can think of it as relating to, I'm going to show in a bit, that is relating to Z, a way to make it look natural in terms of gauging is it's protected by Z2 times rep Z2. And when it gets generalized, what it'll become a state protected by G times rep G. And the way you think about it, it's related to gauging G and getting a dual rep G symmetry.
I see. So in the Z2 times Z2 case, if you want to gauge with a discrete torsion to realize SPT? Gauge Z2 times Z2?
Right. So the discrete torsion would be trivial here in this case. Yeah, you could also add that, but we didn't consider it.
Okay, thank you.
Yeah, it's a specific case of choosing a trivial discrete torsion. Any other questions? Okay, so going back, so the Z2 symmetry, and I want to be super pedantic so that it's clear what I want to distinguish between Z2 and rep Z2 on the lattice, even though they are sort of isomorphic, is that there are two elements, and the action of the symmetry Z2, I'm going to choose it to act by X. And that is natural because, well, these two group elements, what they do, identity, of course, shifts enough. I have a Hilbert space where it's CZ2, and the basis elements are given by S, where S is 0, 1. Okay. And of course, the identity does nothing, but X is going to shift S to S plus 1. And so the symmetry Z2 will act as a shift. Now, on the other hand, how do I want rep Z2 to act? I need to write down a different model, which is the, I could say, dual transverse field Ising model, where I instead have a longitudinal field, but my Ising term is now XX. And now this model will have a rep Z2 symmetry. and rep Z2 has two elements, of course, the trivial element, but now it's acted by a poly Z. And instead of thinking of it as a Z2 symmetry, we should think of it as a rep Z2 in symmetry in the following sense, that this guy, the rep Z2 has two elements, and you should not think of it as group elements anymore, but you should think of it as irreps. And so you should think of the Z acting as the sign irrep instead of applying a shift operator. And that's exactly poly Z, because depending on the group element, you're going to assign a phase, which is exactly the sign representation, that -1 to the S. So that's why the Z basis is more natural to describe rep Z2 symmetry. And of course, in this case, we know that Z2 is equivalent to rep Z2. We know that because there's a Fourier transform that connects the two. Quantum information people like to call this Hadamard, which is this operator that maps X to Z. But I just want to make the different state the difference out front so that they look different on the lattice. So that's how we're going to distinguish Z2 from rep Z2. Okay. So now let me introduce the model of the 1D cluster state. It's the unique ground state of a particular Hamiltonian. And the Hamiltonian is written as, on a 1D chain, it consists of three body terms, Z, X, Z. And all the terms commute. And so on the closed chain, you can convince yourself that it has a unique ground state. It's given by the +1 eigenstate of all these poly operators together. And it's protected by, it has Z2 times Z2 symmetry, which is the product of all odds of X and all even of X. So you can see that it commutes with the Hamiltonian because it commutes with these two Z's, for example, when you act on half the sites. Okay. And is an SPT actually protected by Z2 times Z2 symmetry, and is given by this A1 cup A2 class in H2.
Question?
Okay. Yeah.
Are you on an infinite chain or finite chain?
Let's assume it should not matter for my discussion here. Is there a concern?
Well,
but I'm
the
on periodic
separation
boundary
into odd and
conditions.
even is not meaningful if it's a closed chain with an odd.
Oh, I see. Well, closed chain, but even sites, you can still make sense of that.
Okay.
But we can assume infinite for simplicity. Okay. Now the representation I actually want for my cluster state, which will more naturally generalize when I go to finite groups, is I want to Fourier transform the even sites. And what that does, it makes all the terms either pure X or pure Z. And there's a jargon in the quantum information community that people like to call CSS, and it stands for three people's names: Calder, Bank, Shore, and Steen. And it just means that all the terms are either pure X or pure Z. So if you don't mind, let me just use that jargon here. And if you do that, what happens is all the odd sites will now look like XXX. And then all the even sites will look like ZZZ. Okay. And now the symmetry will be Z2 times rep Z2, where the odd sites are acted by X and the even sites are acted by Z. And this is the basis I want to use. Okay. And the goal is to generalize this to a CG. And roughly the answer we're going to get is I need to first generalize what X and Z mean in the finite group case, but it's going to roughly look like this. There are more technical details later. But the key tool we're going to use is the cluster state is related to gauging. Okay. And people in condensed matter sometimes use the term Kramers-Wanier transformation when they describe this. Okay. So before I do generalized polys, let me quickly review what the Kramers-Wanier transformation is. And I'm going to write this on the left, and I'm going to write the generalization for the group G a bit later. So what people are usually familiar with probably is the map from Z2 to Z2, where you map the spin chain back to itself, where you map the transverse field to the Ising term, and then also the Ising term back to the transverse field. What I'm going to do is slightly different, which is I'm going to Fourier transform the right-hand side so that it does not map to itself, but it'll map a Z2 symmetric model to a rep Z2 model. So Xi will map to Xi plus 1, and the Zi plus 1 will map to Zi. Okay. So why do I say it maps from Z2 to rep Z2? Well, because if I define this operator which maps as such, it's just an it's an isomorphism of two operator algebras. It has this Kramers-Wanier operator has a right kernel and a left kernel. The right kernel is the product of all X operators because it maps to a product of XX, which on a closed boundary condition, so let's assume it's periodic, is equal to 1. There's some subtlety about the boundary condition, but let me just assume everything is in the even sector and everything is periodic. So everything maps nicely. So this is this thing over here is the Z2 symmetry I mentioned earlier. And it also has a left kernel, which is rep Z2, because the product of Z on the right comes from a product of ZZ, which is equal to 1 on the left-hand side. So this is the right kernel. Okay. Now, if you restrict to particular states that satisfy these constraints on both sides, you can sort of, you can tell how the states map. And the way, roughly, the way we understand it is the states maps spins to domain walls. So suppose we're given an Ising configuration. What we want to do is we want to map it to the present or absence of the domain wall. And in Z2, we just sum these two together. And we are going to consider a dual Hilbert space living on roughly on the half site between these two. So we're going to assign a 0 or 1 depending on the presence or the absence of the domain wall. So how do we implement this? Well, we can implement this by a certain operator that does the job. I'm going to write that as a matrix product operator. So the idea is I'm going to have a bunch of tensors, and then I'm going to glue them together in a specific way. Let me write down what the answer is first. So I'm going to input it from this side, and this is my original Hilbert space, which has a Z2 symmetry. The output is going to have a rep Z2 symmetry, and it's going to come out from this side. Now, let me specify what these tensors are. You can think of the first tensor as something as so-called a copy tensor, where if I have inputs A, it's just going to output the same group element A. So for example, you can think of it as a delta function, where it copies A to both the B and C legs. And the second tensor, I'm going to call it the sum tensor. If you have A and B as an output, it's just going to output C as the sum of the two. Okay, so let's see why this works. So if I have Si here and Si plus 1, the first tensor is going to copy both of these to be Si. It's going to copy both of these to be Si plus 1. And then the sum tensor is going to add the two. So we get what we want on every output leg. So my claim is this is the Kramers-Waniya operator. So it maps it maps correctly at the level of the states that are symmetric under these constraints. Now let me convince you that it actually does the right thing at the level of the operators as well. In particular, X maps to XX and ZZ maps to Z. Okay. So these tensors were a bit hard to write, so I just wrote them out in advance. The key observation is that when I define this copy tensor, you might have noticed that the states that satisfy this condition, you think of that as 3 spins in some sense. You can think of this as 0, 0, 0 plus 1, 1, 1. So I'm only thinking about Z2 spins here. So the only states that satisfy this are when all of them are 0, all of them are 1. But you can sort of think of that as exactly as a 3-site Z2 ferromagnet. So they're all pointing it up or pointing it down at the same time. So in particular, this tensor is satisfied by an Ising term ZZ and also a Z2 symmetry that flips all the spin at the same time XXX. So in particular, this tensor has the following identities. Since, for example, ZZ acting on this copy tensor is equal to itself, you can multiply Z on one of the legs, which means that you can move Z freely through any of the legs. If you have Z acting on one leg, you can move it to act on another leg. And similarly, if you have X acting on one leg, you can move it to both legs. Okay. The second observation is that the sum tensor is actually the Fourier transform of the copy tensor. So this needs a little staring, but what is the sum tensor? It's all the states that satisfy the sum condition that A plus B is equal to C. If you write them all down, you notice that that's just all the states would have an even number of ones. But that's exactly the plus 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 state summed with the minus 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 state, because plus is 0 plus 1 and minus is 0 minus 1. If you expand it out, if there are an odd number of ones, the minus sign will sort of cancel it here. So you can convince yourself that this is correct. So now we know that it's just a Fourier transform. It just means that you need to swap these identities whole by swapping the row of Z and X. So there's some symmetry between the copy tensor and the sum tensor. Unfortunately, this won't be true for the non-abelian case, but this is true for at least Z2. So now we can see that now let's use these identities to show that it does the right job. So suppose I start with my Ising term ZZ on this side. Let's use these identities to show that this is doing the right thing. I can push Z through using this rule here. I can push Z through to this leg here and do this leg here. And then I use this rule to push it up to a single Z. And similarly, if I start with X, I can use the rule to push it to 2 X's, and then I can push it up individually into a single X. So that shows that the operators act correctly as they should. Okay. Now, finally, the observation is that the Kramers-Waniya transformation, as I've defined it, it maps ZZ into Z, and it maps X to XX. And now if we think abstractly as just flipping down or flipping up half of the legs, I've turned an operator into a state. And this state is exactly the cluster state I defined earlier. So the property is that the eigenvalue of ZZZ as a 3-body operator is equal to 1, because I can push this as such. And also the 3-body operator XXX is also 1, because due to similar tricks, this is equal to 1. So you push them down and they all cancel with each other because z squared was 1. So this is exactly the state which is satisfied by the cluster set I introduced earlier. So this is the connection between the cluster state and the Kramers-Wanier transformation. And so if you think of it as an isomorphism of operators that perform gauging, this gauging quote unquote operator is closely related to the cluster state. And now we'll see how this generalizes to the finite group case, where we take the Kramers-Wanier operator that maps G to rep G. We will flip half the legs up. That'll give us a state that's symmetric under G times rep G. Okay, any questions up until now? Okay, if not, let me go back up here and explain the generalization of Pauli operators to finite groups. So what I'll need to generalize is I need to generalize what I mean by Pauli X and Pauli Z. And our Hilbert space will now be CG. So it's labeled by group elements where G is in the group G. And let me just, for shorthand, label G bar as G inverse. Okay. So the role of X with shifts operators will now need to be generalized to left multiplication and right multiplication, which I denote L and R. In some of the literature, including some of the previous papers that I mentioned, they're sometimes denoted like this. But I'm going to stick to left and right L and R today because it's easier to stare at. And what left acts as is just performs multiplication by G on the left, and right multiplication, I'm going to choose the convention where it multiplies by G inverse instead of G on the right. And just to make it super clear, the dagger of LG is just multiplying by G inverse, and same for right. Okay. Now the X one is obvious. The Z one is a little less obvious. But previously, I mentioned that Z corresponds to irreps of the group. And in particular, for rep Z2, it acts by multiple sign factor. So it turns out the natural generalization of Z is to label Z with each irrep of the group, where gamma is an irrep of G. Sometimes I'm going to be sloppy and replace this with rep, but what I really mean when I say gamma is in rep G is I just mean the simple object, just irreps. Now, instead of just, for example, X, we know that this is sort of like an operator. It just takes, so it just maps operators as such. For Z, it's going to be a bit more subtle because now there's going to be an extra subtlety is that there's going to be a sort of internal index, which I'm going to label with red. And the dimension of this internal index is going to be the dimension of gamma. So there's some internal index you have extra internal index you sort of have to keep track of, which depends on the representation you're choosing. So in the abelian case, everything was one-dimensional. So this leg was one-dimensional, so we didn't have to care about it, but now it becomes important. So let me define what Z gamma acts as. For Z gamma, it acts on a group element G, and it's going to assign a matrix to it, gamma of G. So gamma is the matrix representation of that irrep. And it now has this index, matrix index IJ. And that's what I'm denoting graphically with this red leg here. Okay. And Z of gamma, the dagger of Z gamma will actually be Z of gamma bar, the conjugate representation. Okay. So now that we have that, let me show that how we can represent G symmetry and rep G symmetry in such a model. So for example, X will be used to represent the G symmetry, and you can define some generalization of the Ising model, which has G symmetry. So instead of having a ZZ, so we know that we wanted to sort of have a ZZ term and an X term. Now what we will have is we will now have to sum over left multiplication, and we not only have to sum over all sites, but we also have to sum over all group elements G. And now if I just had this transverse field, you can convince yourself that left and right multiplication commute with each other, so it already has a right multiplication as a symmetry. Whether you choose right or left as multiplication depends on your choice. Sometimes you can have both, but I'm going to just restrict to the case where you only have one. And now the term we want here is we want something to sum over all the irreps, and also sum over all sites. And that term turns out to be the following, gamma bar and gamma, and you also weight it by the dimension of that irrep. And you can use some identity to show that this is actually just selecting for each group element on it's just a delta function that makes sure that the sites I and I+1 have the same group elements. Importantly, you might notice that there's something wrong here, which is there's this matrix sort of element sort of dangling around. So to make this correct, I actually have to trace over this internal index. And so the Ising term, I actually have to write down in this case, sort of has to look like this. It has to be ZZ, and then I contract this index together, and then I trace over. So this is what the Ising term would look like. Sorry, and this is supposed to be a dagger here. So it looks something like Z dagger Z, and then I have to trace over this internal index. And this model, you can check it has G symmetry. If you gauge this model, you'll get a model with rep G symmetry. Let me call it the rep G Ising model. And maybe if you want to get everything to be a projector, you sort of have to weight it by 1/G. That's a subtle point, but not very important point, but just for clarity. The rep G Ising model, the Z will sort of map to a single Z. And you have to trace. Sum over all sites. And also you have a transverse field, which is given by right multiplication times left multiplication. Now, this model has rep G symmetry. How do I define rep G symmetry? Well, in the previous case, we saw that it's a product of Z's. So it turns out that rep G symmetry will sort of act like this. You sort of take the Z operators for each gamma. You contract them all together, and then you take the trace. So this is what the rep G acts like in the lattice model.
So Nat, excuse
yes.
me, is in the G Ising model, is the G action on the states by left action or right action?
By right action. So in this convention, I'm choosing it to be right action.
Ah, I see. Okay.
It could be left, but doesn't really matter. You can just conjugate every site to get it back to left action. But yeah, depends on the basis you chose for the Hamiltonian. Here I'm choosing right action. Okay, so now for rep G, if I wrote it in terms of operators, that would be trace, and let me call this operator B gamma. And you might notice that this operator is actually not unitary, and that's the rep G symmetry action. How does it act on states? Well, if I have G1 to Gn, and I act with this B gamma, what I'll get is I'm going to get trace over gamma acting on G1 all the way to Gn. This is now a number because I've already traced over it. but this thing is just the character of gamma applied to all these matrix, the product of all these matrix elements. So you can see that since the character is not, it does not need to be a root of unity anymore for a general group G, this operator is not unitary. And you can check that if you had two B gamma operators and you sort of stack them over each other, for example, visually it would look like this. So if I had B gamma I, B gamma J, I stack them on top of each other, what will happen is B gamma I, B gamma J is equal to, and the product is given by the stacking in the direction I mentioned. You would get exactly a sum of other operators where this multiplicity here is just the fusion coefficient of rep G. Okay.
So is something known about the phases of these Ising models?
Right. So for example, I've only written down two terms. You can write down more terms, but if you have this term turned on, then it'll be the rep G symmetric phase. And then this one will be the one where rep G is completely broken. So it's because it's just dual to the symmetric phase. If you use the mapping, it'll be dual to the symmetric, completely broken phase of G and the completely symmetric phase of G.
And the transition is some conformal theory, which is rep G symmetric.
I guess so. Whatever this transition is, but I don't know whether people have studied whether this is a conformal theory or not. It's not clear to me whether you can have a gapless theory in general, but also you can write down terms for each subgroup, which I've left out, but subgroup and cocycle. You can also write down an appropriate term here if you want. Yeah, I didn't do that here.
So when you consider rep G symmetry, you can map untwisted sector Hilbert space to twisted sector Hilbert space. Do you consider these kind of actions? So the action you're describing is not the complete action. It's piece of the full action.
Oh, you mean how do I twist rep G?
Yeah, but so you get this twisted sector Hilbert space, but the action is also from untwisted to twisted. You can have actions like this.
Oh, when you do the mapping.
Yeah.
I think in principle you can do that. I have not tried to do that exhibit myself, but I think it's possible.
Okay. Thanks.
Let's see, how am I doing on time? Okay, maybe I need to speed up a bit. Okay, now roughly what I want to do is this Kramer's 1A of G. How do I generalize the previous case? I wanted to map G to rep G. And roughly the idea is you take two spin configurations, which are now G valued, and now you're going to map them to the domain wall variable, which is you look at the difference in the group sense. And I'll have to show in a bit, but you can show that the right kernel is going to be symmetry, is going to be this, because if you multiply every group element by something by G on the right, they're sort of going to cancel over here. So you can see that this thing will map to 1. And also you can show that this rep G, where you product over Z gamma, does nothing on the left. So it is a left kernel. Right kernel. Okay. And roughly the way the operator looks almost looks the same. This tensor is still going to be the copy tensor, where if I have group elements G, H, K, it's going to just set them all equal to each other. And this operator, what it's going to do is, depending on the input G and H, it's going to multiply them and set it to the output K. So one quick remark is that you might notice that these tensors are exactly this tensor is exactly multiplication, where you multiply G and H and output K. And this tensor is actually co-multiplication in a Hopf algebra. So you might even see that this construction, you can actually generalize to a general Hopf algebra by replacing these tensors with corresponding multiplication and co-multiplication. Okay. And based on the definitions of the tensors, you can show the following identities. I wrote them down in advance to save some time. But basically, the rules for pushing Z through follow similarly, but you have to keep track of this extra internal index. And the way you push X now depends on has sort of different rules from left and right, and you have to keep track of them properly. And for pushing X, for pushing X through, it now sort of depends on left or right. There's sort of some difference. I sort of made some choice here when I said that G times H is equal to K. I'm sort of giving a preference to this side, and that sort of made that sort of broke the symmetry between left and right. And lastly, the way you push Z, now you also have to keep track of this internal index. But based on this, you can now show that if I push sort of this Ising term, and let me leave it uncontracted, ZZ through, you will similarly get a single Z, which is what I want. And if I push left through, I'm going to get roughly right and left. So that if I input my model to be the G symmetric model, my output is going to be the rep G symmetric model that I defined earlier. And now basically what I want to do is flip the state down. So I'm going to get a state. So I can define a Hamiltonian, which has roughly XXX on all the odd terms, now generalized properly to group G. And now the ZZZ generalized properly. As two terms of the Hamiltonian, I imposed energetic constraints on them. And these terms actually all commute. So I'm going to define a commuting projector Hamiltonian, which contains of these terms. And I sum over all G and all irreps. I'm going to get a unique ground state, which is exactly this cluster state I'm talking about.
Nat, I have a quick question related to your earlier comment. So is this cluster state parity invariant for general?
By parity, you mean?
I goes to minus I, spatial parity.
Oh, no, because there's a difference between odd and even.
Right. No, but also because this white tensor, right? You refer to two of the legs over the other. So
if you flipped it and shifted, is it the same one? No, it won't be. So we can even do this for the finite group case, sorry, abelian case. And you're going to get an SPT, and if you reflect it, you're going to get an inverse SPT.
Oh, of course. I see.
Yeah. Okay. So let me now quickly show the symmetries and this will tie directly to opening up a chain and getting edge modes. So in the abelian case, what we do is we have X symmetries on the odd sides, and we push them through using these rules to this virtual level, and then you sort of get two X's, and then we can use this rule on the sum tensor to sort of cancel these out pairwise. So you can see that this is the symmetry. Similarly, the rep Z2 symmetry, but also you push it to the virtual level, everything cancels, so you show that it's a symmetry. Now, if you open the chain, what will happen is when you push this through, you're going to get some edge mode left with axis X at the virtual level, and Z for the virtual level for this is Z2, and this is rep Z2. And that's sort of the reason why this cluster state is the non-trivial SPT, because we know that XZ anti-commutes, X and Z anti-commute, and so you get a projective representation. And from this, you can argue that each edge will have a twofold degeneracy. Okay, So now let's see how this generalizes. Nadi?
I'm trying to understand what you're doing in terms of gauging. So can I do that for any model that has the symmetry group G? Or so I'm
in the way
I'm having mind some Hamiltonian. So can I do that for any Hamiltonian that has the symmetry group G? Or
yes,
is it
by you mean by using this map, you can conjugate any, you can take any Hamiltonian term, you conjugate it by this Kramer-Swania operator, and you'll still get a local term. Given that it's symmetric, you'll get a symmetric term on the rep G set.
So if I have some spin system that has a global symmetry G, will this be the same as gauging the symmetry G? Or will this be something different?
Yes. You can show that they're equivalent by doing this minimal coupling, and then setting all the Gauss law to 1. You can actually show that it's equivalent to applying this operator. I haven't shown that, but
you have or have not?
I'm not going to talk about that, how to do that here, but it can be shown. Yeah, and I can explain that to you person later if you're interested.
Okay, thank you.
Okay, so how does this generalize to the non-abelian case? On the odd sides, I'm going to have right multiplication, and using the rules, they sort of push down to the virtual level as R and R dagger. Let me suppress the G here, and they sort of cancel again. Now, if I have an open chain, what's going to happen is I'm going to have it act as R and R dagger on the two edges. The Z tensor is a bit more subtle because the rep G symmetry is a bit more subtle because now I have this virtual index I have to keep track of. And now the difference is on an open chain, I don't need to contract, sorry, in the case of the, when the chain is closed, I can fully contract this tensor. But if I have an open chain, the difference is I don't need to keep this, I don't need to contract this index. I can sort of leave an index ij dangling at this edge. And once you push through, what's going to happen is you're going to have a Z operator acting at the virtual level on each edge, Z and Z dagger, but you're still going to have this sort of open tensor as such. So you're still going to have act like this. So what does the boundary symmetry action look like? So in the abelian case, we sort of have something like for Z2, it acts as X left and X right. And for rep Z2, it acts as Z left and Z right. And these two operators commute at the commute, but if you factor it to each edge, they anti-commute. What does it look like here? Roughly, the boundary symmetry looks like right multiplication for the left and right edge for each group G. And ZZ dagger with this index, virtual index ij. And you can show that these two operators commute. But what the funny thing that happens is now if you restrict to each edge, and now this, since the Z tensor is sort of contracted, you can't really factor it onto two sides. So let me just tag both of them along for the ride. So if I commute right multiplication through this Z, let me keep both edges, left and right, ij, I'm going to get something that looks like Z gamma. And then I have to contract it with gamma acted on G. Right. So the funny thing, you don't get a phase anymore, but you get a matrix, which is sandwiched between the two edges. So once you move the right multiplication through, you sort of get an extra matrix hanging out over here that you have to contract. And that makes the story a bit more complicated. But what you can show is that actually there are the ground state degeneracy on an open chain is due to this weird commutation relation is actually G squared. So it generalizes from the finite group version case that it'll just be G squared. Okay. Let's see. I might not have time to talk about topological response. So let me skip a bit to the talking about how, in what sense this is a non-trivial SPT. Johan, you had a question?
No, I was about to ask the same question, but
oh, okay. Yeah. So let me skip the topological response. So you might ask, we see that this thing on an open chain has edge modes. In what sense is this a non-trivial SPT? So first we might want to ask, what is a trivial SPT? And there's already some subtlety for defining it. For the group case, there are two definitions we usually use. One is we say that under stacking, it's the identity element in the group of SPT phases. But for non-invertible symmetries, this is not well defined, because in order to stack, you must be able to restrict to a diagonal symmetry. And for rep G, you cannot do that. Rep G times rep G doesn't have a subcategory, which is rep G. So this one, we cannot use this definition. The second one you might choose to define is the phase in which the phase in which contains the symmetric product state. Now, this definition is also subtle because you sort of have to make a choice of first pick a Hilbert space and pick a symmetry action. So the SPTs really sort of form a torsor, but if you've made this choice, then you can specify there is a phase for which the symmetric product state lives. And if you want, you could call that the trivial SPT. So just because this notation is ambiguous, let me just call it the phase containing the symmetric product state rather than the trivial SPT. But if you want, you can think of it as trivial, but there are just some subtleties to keep in mind. But if I make such a choice, the claim is that this cluster state is a distinct SPT from the symmetric product state. And what that means is that if I take the symmetric product state and put it next to my SPT, there's going to be an edge mode, and that's the edge mode we've been seeing. Because on the left of this chain, I would have a symmetric product state, and then I interface it with my SPT, and the edge mode is this interface because they belong to two different phases. Okay. There are also two interesting comments to make about terminology. One is this phase invertible? Again, this is similar to the first sense in which to say whether something is invertible, you need to say, is there an identity of the group? And in this case, it's not well defined without the notion of stacking. Second is this phase short range entangled? Meaning without the symmetry, is there a circuit that connects it to the trivial product state? And this turns out to be the case. So you can indeed, if you forget about the symmetry, there is indeed a finite depth circuit that connects it to the product state. I'm not going to write it down explicitly, but we do in the paper. Okay. Now, how do I show that this cluster state is distinct from the symmetric product state? How to show that, I'm going to use a duality argument. And how to show is non-trivial. The idea is basically to gauge rep G. And actually, this argument already works for Z2. So let me just do that. And it turns out that for the general G case, you just need to keep track of the X's and Z's properly. So there are two Hamiltonians that I'm interested in. The cluster Hamiltonian I mentioned, which has XXX on the odd terms and ZZZ on the even terms. The trivial Hamiltonian has a product state and is given by X on the odd terms and Z on the even terms. So the ground state is just going to be the plus state for odd and the identity state, the group identity for even. And the idea is we're going to gauge rep G. So we're going to gauge rep G acting on the even sites. That'll sort of turn Z into ZZ and XX to X. So what do we get? We get two Hamiltonians, which are now symmetric by G odd times G even. And I'm going to argue that these two are distinct states. So on one hand, the trivial state gives us X odd and ZZ even. And the cluster, if you gauge it, what you get is X odd, X even, and Z, odd, even, odd, even. So let me put back the indices here. This is even, odd, even, and this is odd, even, odd, odd. So if you gauge rep G, this is the Hamiltonian you're going to get. It's now protected by G times G. And you notice that for H1, the ZZ term breaks the G even symmetry. So this full symmetry is broken down to a subgroup, which is G odd. On the other hand, my claim is that in H2, both G odd and G even are broken. And in fact, the subgroup that is preserved is a different subgroup, but it's the diagonal symmetry, which acts as a product of both even and odd at the same time. So because I've mapped this to two different symmetry broken phases, it means that once I gauge it back as G times rep G phases, they must be distinct phases. And it turns out there's a simple way to see this, actually. We can perform a basis transformation to map H1 to H2. So define a unitary, it's called control multiplication, control X, from the odd to the even sites for every odd even pair. What it does is it maps every X odd to X odd, X even, and Z even to Z odd, Z even. It's possible to do this for the group case, but you have to be more careful. But what happens is you can see that by applying this map, X odd becomes X odd, X even, and here Z even, it becomes Z, 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 Z. So at the level of the Hamiltonian, this maps H1 exactly to H2. And also the odd symmetry under this symmetry transformation get maps to G diagonal. So, and while also leaving G even invariant. So I've shown that they map exactly into each other if you redefine the symmetry. So since in this phase, only G odd is preserved, since G odd is mapped to G diagonal, in this phase, only the G diagonal group is preserved. Okay. And it turns out that this unitary, if I mapped it back to the G times rep G side, since it's that gives you the circuit that maps from the symmetric product state to the cluster state. Okay. Let me just try to quickly wrap up. I have one comment about the relation from this picture to the SymTFT. So H1 and H2 that I mentioned earlier, just now, you can think of it as having a quantum double of G times G. And for the reference boundary, what you want to condense is you want to condense all the charges. Let me denote them E. And for the symmetric state, we've broken G even. I'm calling them 1 and 2 here. So we condense E2 here, and we condense all the fluxes for the first copy. Whereas in H2, this is the reference boundary. We still condense E1 and E2, but what we do differently, roughly, is we condense this pair, M1, M2 bar and E1, E2 bar. For the non-abelian case, you have to be a bit more careful, but what I really mean here is you condense pairs AA bar for every anion A. So what I really mean is if you sort of unfold this boundary, this gives you the trivial interface. Okay. And now if I want to map back to the symmetric product state by gauging rep G, all I have to do, right, is to replace E on the second copy with the fluxes. So now my reference boundary, this will give me a G times G symmetric state. And I'm basically condensing the same things on this side. So this is now the SymTFT version to realize the cluster state. And this one will realize the symmetric product state. Okay. So what are the things I didn't cover? I have one more thing to add to the list. It's the topological response. There's also string order parameters for these phases. We also showed in our paper that these cluster states are interesting for quantum information people because they can be used for measurement-based quantum computation. You'd sort of perform some measurement in this virtual space, and then you can perform computation. This is known for cluster states that are generalized to a abelian group, but it was not known how to, well, people really didn't really think of it, even this model in particular, but we actually show this for a specific subclass. For example, if it is a semi-direct product of two abelian groups, we can actually show that you can also perform measurement-based quantum computation. And the idea actually turns out to be that the Kramers-Wanye operator of G can be decomposed as a two-step gauging, where you first gauge the normal subgroup and gauge the quotient group if you input an appropriate unitary. And from this, you can actually decompose the corresponding cluster state into two rails, one consisting of the normal subgroup and one consisting of the quotient group. And then you perform computation independently in each rail. So that's just a fun fact we found. Okay. Let me just conclude with some interesting questions for future work. So there exists this unitary I mentioned that prepares this cluster state from the symmetric product state. In fact, you can keep applying this unitary and get more models. And the number of models you get is actually the exponent of the group. So it's just the least common multiple of all the group elements. So for example, let me choose G equals S3. You will get this number is 6, but it turns out that if you try to count the number of SPT phases protected by G times rep G, there are actually only 3 of them. So a curious question is, it means that these models, some of them must be equivalent to each other. I've only shown you if you apply the unitary once, but you can apply the unitary multiple times. How does this equivalence happen? We still don't really know it. A second question is, you can generalize these states to Hopf algebras where you define the appropriate multiplication and co-multiplication tensors. And there it's not even clear whether there are unitaries connecting it to the symmetric product state. So it would be interesting to see how do edge modes work there, or how do a lot of these tools generalize. Okay, so let me stop there.
Great, thanks very much for a nice talk. Other questions? Maybe I can start off with this last point. To this generalization, Hopf algebras would be that you start with some general fusion category symmetry and try to do some similar gauging of that on some of the sites.
Right. What I really mean here is for a Hopf algebra, you can define the co-multiplication multiplication. You just sort of take these as tensors, and now you just naively just write down this state that I mentioned.
Okay.
There might be a relation to gauging also if you flip half the legs down. I haven't thought about that, but also might be relating to gauge Hopf algebra symmetry. But
there's often slightly more general question. So there are these, if you feed in a fusion category symmetry, there are these lattice models by Fendley, Arson, and Long, which sort of manifestly have that fusion category symmetry. Can you say a little bit how those models relate to the things you've discussed and what the distinction between what the advantages of that construction versus this is?
I guess you're referring to sort of this anion chain construction.
That's right, yes.
The difference, I feel, I'm not, maybe someone can confirm if this is correct or not, but for the general anion theory, that might correspond to a weak Hopf algebra, but here it's sort of specific to a Hopf algebra. And I think what happens here is that you realize it in a tensor product Hilbert space, whereas for a general anion chain, you might have some constraints on which what are the states you're allowed to act on. It doesn't factor into product.
That's
so
true.
that might be special for choosing a Hopf algebra as an input rather than a general fusion category.
Okay. Any other questions?
I have a question. So in the more general case, when you generalize to other Hopf algebra, is it always the case that that there's a product state that's invariant under the non-invertible symmetry?
Yeah, that's a good question. I haven't looked into that yet. So I don't know the answer. Yeah, that would be the next thing we would want to do. Yeah.
Right here, yeah, it's kind of interesting that, well, I mean, your setup is clear that there's a product state invariant under G times rep G. So it's hard for me to believe that's always the case. When that's not the case, I guess we cannot even say what is a trivial SPT and what is not.
Right. Yeah. Yeah, I think it's worth thinking about.
Yeah. And from the mathematical point of view, if you just look at the set of fiber functors for a given fusion category, there's generally no sense that one fiber functor is more trivial than the other. They're typical.
Right. Yeah. I guess here as I mentioned, you really did make a choice. You did really make a choice of choosing a Hilbert space and choosing a symmetry action. You could have chosen a weird symmetry action, which sort of permutes the different SPTs. And under that transformation, you could have called it would turn the product state into something else while keeping, maybe here, the rep G symmetry might still look the same under this symmetry transformation, and you can't really tell the difference. So there you might be able to permute them.
So if you realize the symmetry as a representation of Hopf algebra, then there is a notion of a trivial one, which is just dimension of the representation. But then, of course, it depends on which Hopf algebra you choose. So there are various notions of triviality depending on that.
Sorry, are you talking about the symmetry action or the state, the phase?
Yeah, I mean, so our symmetry category is representation of some Hopf algebra, though the Hopf algebra may not be unique. But once we pick one, then there is a trivial functor that we can define, which is just a representation goes to the dimension of, to the underlying vector space. So it's not canonical, but there is a notion of triviality for sure.
Okay, that's good to know.
Nadi, you have a question?
Yeah, so and for which groups does it work? Is it for all groups, or does the group have
finite groups?
Finite groups. What about discrete infinite groups? Or
that's a good question.
For example, U1 or SU2?
Yes. Yeah, I'm not sure whether this will work for U1 even. I haven't thought too carefully about it. There are subtleties with the Hilberts that if you naturally use this construction, you'll have sort of an infinite Hilbert space. And it might be possible to define this map, but I'm not sure whether yeah, it could be possible. Yeah, I don't think it's ruled out, but yeah, I haven't thought about it yet.
what you said is about the infinite discrete group or about continuous groups? I asked two separate questions. One,
infinite discrete group because well the rep sorry, infinite discrete group. Yeah, I mean because the rep of that might be continuous, right? Like U1 and
but
Z.
then there's but then there's another question about compact continuous groups like U1 or SU2, where the representations are discrete.
Right,
there's
but
number of them, but it's discrete.
Right.
And of course, we can also consider non-compact group like SL2, and then it has the two complications.
Yeah, I guess either case you deal with these because it's G times rep G. You're going to deal with this continuous infinite on one side. That might make things settle. So I'm not sure.
Thank you. Nice talk, by the way.
Thank you.
Okay, I don't see any other questions. So let's thank Nat again. I'll stop the recording. Actually, if you